Okay, so let's turn on the light and start talking about the projection transformation or projection matrix or projection in general in linear algebra. One thing that is quite useful, so it's good to know about. So let's start with animation, and because animation lets you understand a little bit how the transformation works. So you can see that the vectors right over here, the vector moves, but it can also not move. And we take the projection of this vector on the x-axis, so we can see how it changes and how the projection changes as the vector changes. Um, this is the projection, the idea of the projection. Take a vector and take its component in the space that you want to project to. Another animation that lets you understand how the projection works is a grid of dots that project into a line. So you can see there are many dots here, and we project all of them to this line over here. We can even change what is the component of each ingredient. We can do it right over here, so it projects exactly onto the x-axis. But you can see how we take the dots and project them into this line that we can define. So this is the idea of the projection. Now let's go through the properties of the projection. So projection takes it's a linear transformation that's going from a space to that space, and there are some very nice properties of the projection. The first one, very important one, is the idempotence, which says that if you take the projection transformation and raise it to the power of 2, you'll get the same as the projection. Now, logically, it's very understandable, because if you project a vector to a space and now you take this space, this vector that you already projected, and project it again to the same space, there would be no change. Think about it. If you have a vector and now you say, I want to project it to here. Okay, so here I projected once. Now if you take what you already did, this one, and project it again to the same space, there will be no change. And if you do it again, there will be no change. Again, no change. So p to the power of any natural number above or equals 2 will give you the original projection transformation. So this is correct. Now, very important thing about it is that if you take the p and move it to the other side, you'll get p squared minus p equals 0. This is usually the minimal polynomial of most of the projection transformations, except the 0 transformation, which is also a projection, and the identity, which also is a projection transformation. Except for those two, what they said now is the minimal polynomial. So this is the idempotence, is a very important property of projection transformation. Now there is also another property, that the projection transformation divides the space and creates image and kernel that, as you can see here, can have direct sum. Namely, there is no intersection between the image and the kernel of a projection transformation, and therefore you can uniquely divide each vector into two components, into its image and kernel of the projection. So it's quite nice. You can see that each vector, you can take it as part of the PV, which is the image of the vector, and V minus PV, which means that it's the kernel. It goes to 0. It's very good. It's very nice because you can take any vector and reduce it to its components, if I talk about projections in 2 dimensions. Now the eigenvalues, you can conclude what are the eigenvalues of a projection. If we think about it, if we think about a projection, or it takes the vector, uh, let's call it to the um, to the space that it's into, or it null the vector. Namely, the eigenvalues are 0, 1. Think about it. If I have a vector that is totally in the space that the projection matrix projects to, so the projection matrix won't change it. Those are the vectors that are related to the eigenvalue 1. You can see that there are vectors in the image of P. Now think about vectors that are totally perpendicular or mm, totally, let's call it perpendicular, in the space that is not in the space that we want to project. Let's call it that way. So what the projection matrix or transformation will do, it just annihilates this component that is not related to the projection. You could see that projection matrix take a V and no, let you define V by V1 and V2. For example, where V1 is in the projection space and V2 is not, let's call it V1 in the image and V2 in the kernel. So when you take V1, you will get exactly V1. Namely, when you apply projection on V1, you will get exactly V1. And when you apply the projection on V2, you get exactly 0. Let's call it V2 and exactly 1 V1. You can see here the eigenvalues. The eigenvalue 1 for image vectors and the eigenvalue 0 for kernel vectors. Okay, so this is a nice property. The eigenvalues of a projection matrix are only 0 or 1. The next property is the trace and rank. So you can see that the rank of a projection matrix equals its trace. Now, remember that trace is something that stays similar between similar matrices. So if you think about what you just say about the eigenvalues, the okay, maybe I won't get it too far away, but the rank of a projection transformation equals its trace, which is the dimension of the image of P. Okay, now there is also subset of projections, which are the orthogonal projections, and it means that projection onto a subspace along its orthogonal complement. For example, think about a Cartesian coordinates where the y-axis is perpendicular to the x-axis. So those projections are symmetric, and the kernel is just the complement of the space you project to. Also, the projection will be positive semi-definite, namely it satisfies the thing. Now, another thing that is nice is that you can present the projection matrix as a block diagonal form. Remember that the only eigenvalues are 0 or 1, so you have a block of this of the 1's eigenvalues and also 0 right over here. Okay. So idempotency, eigenvalues, the composition into space into image and the kernel, as in symmetry and positive semi-definite for orthogonal projections. Those are the properties. Now, if we talk a little bit about the projection, and when I mean by the projection, I want to show you about the formula for the projection. I think I have it right over here. Yes. So when we're talking about the formula for the projection, in the most general way, we can think about it as maybe not in the most, maybe we'll ask for it for the most general. Use inner product to show me the general formula for the projection of a vector, because I want to show you the more general way to see a projection, and I want to use the inner product. This is using the matrix formula, but this is not what I wanted. This is what I wanted. Okay. I want to show you it for vectors and not for matrices. You can also learn the matrices formula for the projection, which is this one. You can remember this. So the projection in a linear operator matrix, you can look on A transpose A minus 1 or inverse A transpose for the projection transformation that always satisfy this idempotency. But this is in a metric form. And you can apply it to the vector right over here in this case. But I want to show you in a vector way, which is this one. You can take a vector that you want to project into a space. For example, A are the components of the orthonormal, or let's take just the base, and in a minute we will talk about orthonormal base. So we take a vector, you want to apply the projection to a base which uses the base like this. But I want to show you this one. This one for a base, general base. Okay, as you can see, I can take a vector and take it to the span of A. So I project it to the span of A. And what I wanted to show you is that I take a vector and take the inner product like we did with the dot product. And I take the inner product with A, and now I divide. This is just because this is not orthonormal. But if I normalize this, this will become 1. So to project V into a span of A, let's call it, you take V, A, and the inner product between A to itself, which is the norm squared of A, and you multiply by A to get the direction. And this is for span of A. Of course, you can use more vectors in the span, but this is for a very simple way. Okay? And now, if the span is normalized, you can just ignore this A inner product A and get this formula, which is much more cleaner. And a more general way, okay, this is not very nice, but a more general way, you can just sum for each vector in the span like they do here, but I like this formula much better. You just take for the first component A1, 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 and now let's say that I have a next vector in the base, for example, A2, so I do plus inner product V A2 divided by inner product A2 A2 times A2, and etc. and etc. Anyway, this was some discussion about the projection transformation, its uses, its properties. It's very useful. And thank you very much. Thank you for ChatGPT for writing it down for me so it can be written in LaTeX and rendered so it will be a little bit more beautiful. Thank you all, and that's it for now.